Hi everyone, I'm going to talk to you about Apache Beam, that is a big data processing framework, and the story of how we change it to make it portable. This talk has two aspects. One aspect is to introduce you into Apache Beam, the Apache Beam model, and the second part is discussing the technical challenges of migrating the current infrastructure we have into a multi-language infrastructure with gRPC. So I am Ismaël Mejía. I am a software engineer that works at Talend. In the project, active as a committer and as a part of the PMC in Apache Beam. And I also am an Apache Software Foundation member, so I'm a little bit like in the wrong place because this is Cloud Native Conf, but well, we have to be friends, all of us. This is open source anyway. So I work for Talend, that is this company who produces data integration software and in open source in part. And I mentioned my company because they were kind to send me here, and also because, well, we are creating new products and we are hiring actively. So if any one of you is interested in these kind of subjects around Beam or big data or DevOps also, please join me afterwards or send me a message or anything. We are based in France, so you have to relocate maybe. Okay, so first we're going to introduce Apache Beam. And Apache Beam is, for me, a really exciting project because it's the conjunction of the two lines of development of big data. Yes. In the one line, Google published all these papers, like the MapReduce paper, like the big table paper, and people in the community from different companies started to create implementations like Hadoop, HBase, etc. And also the community bring new ideas like Spark Deep, for example, with a nicer API or with in-memory processing, and other ideas. So there was like two parallel worlds where people who were not at Google were always looking what Google did. But this changed once Google submitted their SDK for data flow into the Apache Server Foundation. So this is, for me, exciting. This is the point of union of these two worlds. And Beam pretends to be the unified programming model for big data. And two aspects that are really important is that we care about efficiency, but we care also about portability. And when we discuss about unified, it's in the sense of that we can do batch and stream processing with the same framework. This means that we have we don't need special APIs for both worlds. And how do we accomplish this? With some special elements that I'm going to present immediately, and that answer some questions I will see later on. So the first important concept to see how we achieve this is to understand the separation of event time and processing time. When we talk about event time, is the times when event happen. Let's say that you are, I don't know, playing a game on your telephone or listening to Spotify. So when this user interacted, he created an event, and this event has a time associated to it that is normally not the same time at which we are processing the data. This is the processing time. Normally it arrives later, so you can see this plot that we have these events that are arriving, and in an ideal world, we will have data arriving in time and this diagonal line, but well, reality is not like that. We have all these network delays, things are transmitted, so, and even we can have data in retard because, for example, somebody lost the connection to the internet, so this event arrives once, he gets the connection back. So this is the case of a normal data, but this is the case of data that arrives in retard, late. So Beam, to be able to compute all this data in a precise way, but also in a fast way, I mean with low latency, asks 4 questions. These 4 questions are: what results are we calculating? Where in event time are we calculating these results? When are we, in processing time, are we computing, materializing these results? And how we refine the results. Okay, this sounds a little bit abstract, but with some animations it's going to be more clear. So let's see if the first question is what are we doing? So in this case we are just going to sum all these numbers that we saw in the plot. So this happens with the progress of time, that when we are processing, and we are just summing data. But when we arrive to the top, we compute the data. Let's not forget that this computation happens when we decide that it happens. And if we have an infinite source of data, we have to say when and what are we going to include in this computation. So this is the classical batch case. This is MapReduce, for all of those of you who know. But when we have this streaming case, we need to define what interval of time we care about, and we can do this with windows. We can define a window that allows us to, for example, divide the events into chunks. Let's say what was the most listened song in between 10 and 11 today, for example. So these event times get grouped. These events get grouped in time into windows, and then we compute the data with this. Why this? Because we need to have answers faster. We cannot wait all the life for all the events to arrive. So we do this, but again, we have again the same problem. When we trigger the computation of this data, when we do the accumulation, we have to decide. And the way we decide this is by using triggers. And triggers, in this case, we're going to discuss a trigger that is the watermark. Do you remember the straight line I mentioned before? This straight line is the ideal case, but the watermark in the real life is not so clean. It could be on retard, and this line indicates that I won't receive more data. So the Beam connectors send this line to us, this data of the watermark, and then we decide to cut and compute once the watermark says is complete. But as you can see in this graph, the first event arrived late, this red one, and we lose accuracy. Just to compute faster, have low latency, well, we lose a little bit of accuracy, and this is how we refine the model in the last question. So we can tell things like in this code, oh, I forgot to say that the top level is Java, low level is Python, bottom, sorry, in the graph. And the way we compute this is we can tell the system, okay, wait 1 more minute of processing time and bring all the extra data that arrive in this minute. Or you can also count how many elements arrive afterwards that are in this window and also compute. And we accumulate those. So this is a little bit more tricky to read graph, but the idea here is that we can recover this data and have a more accurate result. So that's the whole Beam model. We do all of this by answering these 4 questions, and we can model all these processing scenarios. So we have classical batch like MapReduce, window batching, and streaming accumulation. But in the end, what we did with all this code and pipeline, code was construct a pipeline. A pipeline is a graph of transformations that we go in steps from data that comes from a source, for example, let's say Kafka or HBase or something like that, into data that goes out somewhere. So all these colored boxes are transformations. And we call P collections, P transform those, and P collections the lines that go out of these boxes. What kind of transformations are we talking about? Well, the classical maps transformations that we call Pardo in Beam. We can transform per element-wise, so just applying one function and that's it. We have group by key and reduction-like transformations that are like counts and sums and that correspond to reduce in MapReduce. And we have all these windowing and triggering ones that cover the concepts that we just quickly view to have more precise computation. So in the end, Apache Beam is has 3 kinds of users. There's the end users who write their programs. We have SDK writers who want to create a new SDK that implements the model of Apache Beam. So all these concepts of Windows triggers, etc. And we have runners who are the system that execute this. This graph is interesting because you can see that Java and Python can be languages that are used and run in some of these different systems, like Apache Spark or Flink or Google Dataflow. And so today we have all these runners that are implemented or are in progress at least. You can see that we cover most of the most popular ones. We have in the bottom the 2 cloud native ones that are the Google one, that you don't care about infrastructure at all. You just send your job and it executes, and the IB Streams one. But well, there are also some that are work in progress. But there is something that maybe you didn't think really well when we saw this diagram is that all these are Java-based. All these execute in the Java virtual machine. So the normal question that after someone understands the presentation a little bit more is, okay, so I have a Python pipeline and I want to execute it with the Spark runner. What do? I translate this into PySpark? Say, no. Okay, can I execute Python on a Java-based runner? And the sad question is no. Can I use TensorFlow? This is a favorite of the last year. And run it with the Java pipeline? No. And the last one is, okay, the Python SDK doesn't have a connector for Kafka. Can I use the one that is in Java to connect? And the answer to all of those is definitely no. So let's say that this diagram that I showed before, it was nice, but in reality today we are living in this world. So the only way to execute Python in Apache Beam is to go straight to data flow. So if you have an on-premise thing with Spark or with Hadoop, you cannot run it. So this is a big problem because this is like half of the model that is missing, of the idea at least, of Beam. And this is what the Portability API is for. So the Portability API is a set of services and contracts to be able to do this. But first, let's see what we do today. So this is how we translate, how a runner translates a pipeline written in Beam. So the user just takes the SDK, runs the code, sends the pipeline, that is Java code, it's executed, and it passes by a runner that translates this thing into a native job that you see in violet there. And this native job gets distributed by the own system, let's say Spark or Flink, into the different master and workers. And in the end, the functions that we apply, these part-do functions, that is maps, or these combiners or reducers, get executed. Those are user-defined functions that get executed in a worker in the clusters. No? So this is easy to do in Java because, well, we can play a lot with Java, we can play with reflection, we can extract the data, compose it. But if we think about Python, then we'd have to think in a different way. Sorry, I have a mistake there. So what's the real problem we're fighting for? We are trying to execute code in any language in every runner. But we have some constraints. We need to still support the code that exists. We are not going to change the user part. We need to provision an executed expected environment. I mean, if the person is going to write Python, probably he would like to have all the Python libraries that he has for his project. We need to be performant, have low overhead for this. And we have to support, well, multiple languages, of course, because every SDK can be in a different language. And we want something easy to evolve. So an initial idea could be just to take this initial image on top of the runner and add a process in the side to run Python, like this. I fork up operating system thread and I run there. But then you have all the isolation problems. So the natural idea is to expand this into a Docker container. So that's what this whole idea is about. We add a container so we can have now the user code really into this container. So then when we had this diagram of the transformation, you can see that these two transforms now, if they are written in Python, they will become this. They will become a call of gRPC, but I want to talk about this later, that then executes in the worker the Python code and then get this out. So how can we do this? We can do this with three elements that we call the runner API, the job API, and the FnAPI. So the runner API is a way to represent all those concepts I discussed at the beginning, all these P transforms, all these window, win triggers, all of this we abstracted. Then we have in a message representation way that is going to be protocol buffers. Then we have the job API, that is the way we submit the jobs to the system, and we see their progress, or if we can cancel them also. And there is the FnAPI, that is a set of protocols between the runner and the SDK harness, that is the Docker container. So we decided to use gRPC for this. Why? Well, the classical characteristics of gRPC is it's an efficient serialization format. The uses as an efficient serialization format that is protocol buffers. It supports multiple languages, and at least it supported the two we wanted, Java and Python. It has a really simple service definition, and if you haven't seen gRPC before, I will show you, and I am pretty sure that you are going to understand the ideas quite quickly. And has pretty decent network performance, uses multiplexing for HTTP2, so we are going to be able to mix different things in the same channel. And it has rich communication models like subscriptions and bidirectional streaming. So this is why. This is the new architecture of how we do things now. It's slightly more complex. Now we added some boxes, so we added the job server that allows us to control the job, as I said. We added this artifact staging that I will explain in detail in some moments, and we added also the set of services that are in the bottom, that allow us to control the execution. We are going to detail all of this. Okay. So first, before we send the pipeline in Java code, now we transform this pipeline into this abstract representation in protobuf. This is the first step. But the user still sees the same Java code or Python code. Then, you see, this is an example of the definition in protocol buffers. As you can see, a pipeline is a set of components, and each component has some of the things that these functions do. You can see concepts that I mentioned, like Pardue or combine, and others that I didn't speak about, but you get the idea. There are all these substructures, data structures inside. There is the job server, and the job server in the diagram is a service, and this is a gRPC service. This is copy-pasted, even without makeup. And as you can see, it's quite readable. You can immediately call prepare a job, or run, get the state of the job, its progress, and etc. Also, and this is the first interesting use of gRPC, you can get a stream of results. So you can somehow kind of subscribe to changes in the state or messages that are important to track. And when we say use subscribe all, is the runner who is forking this execution, so it's going to subscribe to see what's going on. All the time we're trying to solve this line of between both. Okay, so now these are the set of services that allow us to control the execution and go with it. The FnAPI. The goal of the FnAPI is just to control the interaction between the runner and the container, the harness in this talk. So first element of this is the artifact element. So this is just to stage things into the Docker container, into the harness. Why we need the staging if we could have a container that has everything? That's a good question, but well, if we are going to distribute this to the general public, we probably will create a general Docker, and then people can stage things if they want, or create their own Docker images. So let's say that this service can be optional if people provide their own images. This is just to put in it some artifacts, and we also have a concept of manifest. And a manifest allows us just to give permissions to these artifacts and to control that they are not corrupted with an MD5. Probably they will change for a more strong hash. Then we have the provision service. The provision service is all about resources in the container, how much CPU we need, how much RAM we need, memory, I mean. If we need disk space and this kind of stuff, all of this goes in the provision API. Then, and more interesting, this is how we send data between both of them. The runner just opens a connection and just sends bytes. Yes, there's bytes going on. And in the container, there is this thing we call coders in Beam that allow to transform from bytes into the representation we have. So people can still be using pickle, for example, in Python, or whatever serialization they want. And this is also decoded back into bytes and coded back into bytes, and sent over the wire. We have also an extra service that is a state API that we'll see further. Okay, so as I said, we send bytes back and forth. And to do this, we use protocol buffers, but we found some problem, some limitation with protocol buffers is that
Depending on the language, the biggest message in protocol buffers can be 2 gigabytes or 4 gigabytes. So to enable compatibility between all, we decided to use the lower limit. And the data works with logical streams, which means that one element can be composed by different messages of buffers, I mean. So this is how data works. This is the state API. The state API is all around having state in the executor. So sometimes we can compute things and give this data back to the container. And this is just mostly like a state store in the runner, but we encourage the container to have a cache also of this to avoid round trips, because, well, we care about performance in this. So that's the idea here, and this is useful to do things like site inputs. That is, for example, when I have a collection of data that I care, like, I don't know, that is a small thing that I can materialize, like an index table. Yes, I can inject this as a state in the runner and even cache it in the container. Okay, so this is the more interesting one. The control API allows us to orchestrate all the execution of things. This is the one who decides, okay, I want to process a bundle that is a set of elements. I send you this little part of the graph, and you execute it, and you give me the results back. This is an example of the definition of the messages and the service. So we send, for example, a request for process a bundle, like you see that, and there will be some other instructions being added here. So this is how we process a bundle. There is some preparation steps first. We just send the FN that are not registered. We get all these inputs and outputs ready to be connected back and forth. And then we just send the trigger to start executing the functions, the user-defined functions. So this is when you execute the Python code. And this process in the end sends the outputs back. So this is more or less how it works. As you can see, there was a game between control and data APIs to do this, that are services, let's say. So finally, we have this login service that allows us just to get the logs of the container out. So we just want to know, because, well, things are happening in the container, but the person who runs the cluster probably is running this on Hadoop or in another different system. He wants to look the logs there. So this is how we extract the logs. So what are the advantages of this approach? Is that we gain this isolation of code. We isolate the configuration of the user environment too, and this is nice because we can provide all the dependencies in one big chunk. Or provide it with artifacts, as we said, as we saw. We can support multiple language execution, and eventually with this we can support mixing pipelines in different languages. And this is important for the TensorFlow example that we mentioned. For example, if someone with Java knowledge just want to add some small part in their processing that makes Python and invokes TensorFlow, we can do this. And also it's important because in Java we have support for SQL, so you can send SQL queries, but this is not in Python, so the Python people can call the SQL by invoking the Java harness. So what are the issues? Of course, all of this has a price. There is some performance overhead that in the first test we did is around 15%. We have extra components. We have a dependency now in Docker, and also, well, it's a little bit more complex, but this is the price to be able to reuse. So what's the current status of this, and what's the future work of this? Current status, we have a universal local runner that is a local runner to test these things. So it uses all this machinery and it allows to invoke Python or any language there. We have an ongoing rewrite of the Flink runner to support the Portability API, and the great news is that just 3 or 4 weeks ago, for the first time, we got the word count of Python being executed in Flink. with all these services. Of course, word count is like the hello world, but it already covers that most of the things are in the right place. We have to go ahead. And also, we have a newcomer that we also weren't able to test with the Flink runner, and this is the Go SDK. So the Go SDK is an ongoing work also in the Beam community. And the word Go SDK, you can see the basic word count in Go, is the first SDK that is natively written to use all of this. And this opens a really interesting opportunity also because if you see, Go produces static binaries, and we can invoke faster things with this. And in particular, we can invoke native things in the container. So this will be quite useful, for example, if you want to do manually some kind of computer graphics algorithms in GPU or stuff like that. I think this is a good use for this. So what's going and what's the future? Well, we're still working in completing the full model support, having a state, having windows, triggers, all these concepts of the beginning. We are discussing how to do metrics correctly with this. I mean, because we need this dance back and forth between the worker and the runner, and the harness. We have not tested yet to invoke I/O connectors between different languages. This example I mentioned of calling the Kafka connector from Python, if it's not existent. Multiple languages pipelines have not been tested, but should work. Of course, all of this means that we are not ready for production. So this is one of the bigger goals in the rest of the year. This is a lot of work, so I don't expect that we have this before at least Q4. And also, we have to support other runners like Spark and make this more user-friendly. For example, because we say in the abstract, yes, I can invoke TensorFlow from Java, but how do you do this in the programming level? We have to refine some things. And finally, we have these validation tests that we already use for the Java native versions. That is like our TCK, that is compatibility kit, let's say. That is the validates runner test. So we have to validate that all of this is correct semantically. So this presentation was in part, to make you, all the people interested in the subjects, aware of this ongoing work, see that it's interesting. I find it's pretty cool from a personal point of view. And just to invite also people to contribute or to come just test and play with these report bugs and do stuff like that. Not only the Portability SDK, you can also come with new ideas. For example, one really exciting idea I found is to implement the .NET SDK. This will bring to the community all the .NET world with all the good things that it has, if someone is interested. Also, you can think about creating maybe a native runner that could be implemented in Go and just replace Flink or Spark or whatever. I mean, there are plenty of ideas to contribute. Not only this, Beam also is doing a lot of other stuff in the site. If you are interested, we're already in version 2.5. The first stable version was 1 year ago, so this is a good moment of stability in the project, a part of the internal changes. And we have a vibrant community of companies and contributors working in the project. And some of the new things we're working on, a part of the portability and the Go SDK, is the move to a new API of connectors that is called Splittable DoFn. That is a really, really cool subject, but no time to talk about this. But it allows to create more rich connectors that Spark or Flink or other systems have. If you have the time, take a look at the presentation on Strata that was some months ago by Eugene. And also there is this schema WRP collections that they are like typed collections to be executed a little bit like Spark does. So this is just to greet some of the people involved in this work. Remember, open source is a team game, so all of these guys worked really hard to put this into place. And this is some reference in case you want to check later on the slides. Thank you. I'm sorry if I went a little bit fast, but my presentation was intended to be for 45 minutes, and I realized today that was 35, so I was like... but at least you have a quite complete deck to check afterwards. So this is all. Thank you. Any questions, maybe? Oh, I see nothing, so... Yes, there is this mic.
this work? Okay. I do the total. Okay, thank you.
This might be pretty new, but do things like Graal VM that are, Java call Python type new virtual machines.
Okay.
How does that play into this?
Okay, well, this is different. We have also, okay, you have it just for okay, I just repeat the question. What about Groovy and all these languages that allow to execute like scripting languages on top of the Java virtual machine? We have support for this already. There is an extension on Beam that is not merged yet, but I'm working on this pull request, so I'm aware of it, that allows to use scripting languages, but just in a primitive way. Let's say that we use it to do Parduce or do things like that. But this is not far. Also, there is Chio, that is the Scala implementation of the Beam model, or the SDK at least. So this exists already. But this is more to cover the whole ecosystem because, well, you can have, for example, Jython to execute Python on Java, but you can use all the dependencies of Python. So this is what we try to achieve. Any other questions? No? Okay. Okay, thank you.